If we talk about scaling, can you explain a little bit the basics? What actually scales? And can you maybe explain to the listeners, how do you scale lasers? How do you scale optics?
At the center of all of our products is something like this. This is an older model, but it's an ultra high vacuum cell with integrated electronics. Inside that ultra high vacuum cell lives our atoms. In most cases for computing, it's cesium, but it can also be rubidium. And increasingly, we're blending the two for our dual species approach. And what we do is we individually address atoms inside this ultra high vacuum cell with lasers, and each of those atoms becomes a qubit. And so the nice thing about neutral atoms is it is a highly scalable modality because we don't need to increase the footprint of the actual QPU. It just stays inside of here, but the processor is growing by adding more atoms into the array. And so I'd mentioned before that we have showcased a 1600 qubit array, physical qubits, and that is by holding those atoms in place using something called optical tweezers and other types of lasers to excite the atoms, entangle the atoms, cool the atoms, and then start to run the logic that you can run on quantum computers, all based on what we do with photonics. And so the ability to scale is one of neutral atoms' highlights. And so already the records on physical qubits are held by neutral atom companies. We hold the commercial record at 1600, and then our friends and partners at Caltech hold the physical record at 6100, and that was using our underlying hardware. So the scalability of neutral atoms, there's a lot to like about it because you can increasingly grow the computational power by just adding atoms to the array. Now, to your question, what does that mean from a laser and photonics perspective? And the answer, luckily, is no. So we use something called a spatial light modulator, which effectively can split atom beams into multiple beams and address many atoms at once. And so you can see one laser coming in to the spatial light modulator and then branching out into many different individual lasers to address each of the atoms. And so luckily it is not anywhere near a one-to-one scaling ratio from add another qubit, add another laser. You can add many, many qubits as you utilize these spatial light modulators, and they're one of the ways that we can really scale the modality efficiently. And I'll just say one last thing is since these atoms are neutral, they don't possess a charge, you can pack them together more efficiently. They don't repel each other. And so you can actually pack quite a few physical qubits and therefore logical qubits into one of these vacuum cells. And we think we can get high hundreds of thousands, if not a million physical qubits in one of these ultra high vacuum cells, which will translate into many, many, many logical qubits.